We continue the chapter Work, Energy and Power. In the previous video, we have discussed about restoring force and spring constant. Already we have discussed about restoring force and spring constant. Restoring force is proportional to F according to Hooke's law. F external is proportional to minus x and F equals to minus k into x, where k is called a spring constant. Now we discuss the expression for elastic potential energy. Expression for elastic potential energy. We have discussed the three different cases, the three different positions. This was the normal position. And the external normal position. There is no any external force acting on the mass, and x equals to 0. The another case was when the spring is stretched by a distance x. In this case, the spring is stretched by a distance x. This distance is x equals to a. The spring is stretched by distance x equals to a, and there was third condition. When the spring was compressed, by distance x equals to minus a. So these were the three conditions. Here the applied force F external and restoring force acts in opposite direction of the displacement Fr, restoring force. In third case, in this case, the force is external force is applied in inward direction and the restoring force acts in forward direction. Fr, the restoring force. So when a spring is stretched or compressed from its normal position, x equals to 0 is the normal position. In this situation, a spring is stretched, and in third conditions, a spring is compressed. So when a spring is stretched or compressed from its normal position, when a spring is stretched or compressed from its normal position, then work has to be done. By external force against the restoring force, because restoring force acts in a direction opposite to the applied external force. So when a spring is stretched or compressed, from its normal position, from x equals to 0, then work has to be done by external force. Work has to be done by the external force in a direction opposite to the restoring force, against the restoring force. So when a spring when a spring is stretched when a spring is stretched or compressed from its normal position. X equals to 0. When a spring is stretched or compressed. In this case, a spring is stretched, and in this case, a spring is compressed. So when a spring is stretched or compressed from its normal position, x equals to 0, work has to be done. Work has to be done by the external force. Work has to be done by the external force. Work has to be done by the external force against the restoring force. Against the restoring force. And we know that F external is equals to F external force is equals to minus F of restoring force. F external, applied external force is opposite to the restoring force. So F external equals to F minus F restoring force, and F external is given by Kx, where K is the spring constant. In the previous video, we derived the result F equals to K into X. External force applied, F external equals to K into X, where K is the spring constant and X is the displacement. Now let the spring is further stretched through distance dx. Suppose let the spring is further stretched through a small distance dx, through a small distance dx. The spring is further stretched through a small distance dx. Then work done dw in stretching the spring through distance dx. So work done dw is given by F external into dx. F external force into dx. Because work done equals to force into displacement. Work done is equals to force into displacement. Now when the external force is applied on the spring, the displacement is in the positive direction. Means applied force and displacement both are in the forward direction. When the external force F applied on a body, on a spring, then the displacement is in the forward direction. And if both have the same direction, then angle between them is 0 degree. So F external into dx cos 0 degree. And the value for cos 0 degree is 1. So F external into dx. The small amount of work done dW is equal to F external into dx cos 0d, and dW equals to F external from first. So from first we can write a small amount of work done dW equals to, at the place of F external we can write Kx. So dW equals to Kx into dx. So this is the a small amount of work done. And total work done in stretching the spring. Total work done in stretching the spring from its mean position x equals to 0. Total work done in stretching the spring from its mean position x equals to 0. Hello. Hello. हेलो, हाँ, अरे काम कर नहीं रहा हूँ, मेरे को फोटो का साथ में भेजिए, मेरे को टीम का फोटो भेजिए, है ना? हाँ, फोटो भेजिए व्हाट्सएप से, तब मुझे पता लगेगा, ठीक है? So total work done in stretching the spring from its mean position x equals to 0, which is given by W equals to total work done equals to integration of dW limit from 0 to x. Total work done W equals to integration limit from 0 to x dW, and the value of dW is kx dx. The value of dW is kx dx. Now k is the constant. It should be taken outside the integral, and integration 0 to x and x dx, and integration of x dx is kx square by 2. So k by 2 x square and limit from 0 to x. So the result we get W equals to 1 by 2 kx square. Once we put the upper limit, then put the minus sign and then the lower limit. So the work done we get 1 by 2 kx square, and this work is done is stored in the body. This work done is stored as the potential energy of the stretched spring. This work done W equals to half kx square. This work done is stored in the stretched spring. As a elastic potential energy, and elastic potential energy is given by U. So U equals to 1 by 2 kx square. U equals to 1 by 2 kx square. Now the formula for external force F was equals to K into x. The value for F equals to K into x. So, and x equals to, from here we get x equals to F by K. So put the value of x equals to f by k. So u equals to 1 by 2 into k, and the value of x is f by k. So f square by k square. 1 times k cancelled, and u equals to f square by 2k. This is the another expression for elastic potential energy. U equals to f square upon 2k. Now k is equals to f by x. When we put the value of k equals to f by x, then u equals to 1 by 2, and the value of k is f by x into x square. 1 times x cancelled, and u equals to 1 by 2 fx. So this is the another expression for elastic potential energy. So elastic potential energy u equals to 1 by 2 kx square, u equals to f square upon 2k, and also u equals to 1 by 2 fx. And if the spring is stretched from initial position x1 to final position x2, if the spring is stretched from the initial position x1 to final position x2, if the spring is stretched from initial position x1 to final position x2, then work done W equals to k integration x1 to x2 and x into dx. So its integration be x dx, integration of x dx, x square by 2. So k by 2 x square, limit x1 to x2, which is equals to 1 by 2k x2 square minus x1 square. 1 by 2k x2 square minus x1 square. This is the work done in stretching the spring from initial position x1 to final position x2. W equals to 1 by 2k x2 square minus x1 square.